Welcome. I am Stephen Harrell, and I'm here with my colleague Amit Ruhela. We both work in the HPC group at TAC, and we are here to talk to you about containerization and performance. The concept of containerization has a long history in computing, starting with Chroot in 1979. The primary motivation for creating container and container-like technologies has always been about changing the view that an application has into the operating system. Sometimes to be more restrictive, but in our case, it enables us to run applications in computing environments they were not designed for. For instance, it is common in scientific software for an application to expect the environment that the original grad student used when they authored the first version of the software. At TAC, we may use a different operating system environment than the grad student used. This can cause a conflict, and we either have to spend the time to resolve these conflicts, or we can bring the grad student's environment to TAC. In this diagram, we can see an architecture stack for containers and virtual machines. You can see the level at which a container works by packaging up the app along with the libraries and binaries it needs. This is especially important because all environments have libraries that can't be replaced without affecting the entire system. And some applications need conflicting versions of system libraries, so there's no way to support one application without stopping support for another application. Virtual machines also have a similar set of features to containers, but they require a second operating system to run. This means they will perform much slower, and as we know, the HP and HPC is high performance, so we can't afford the overhead to run a second operating system. Containerization has many benefits stemming from the standardization of the compute environment. In one way or another, all these benefits in the diagram are important for HPC, but I'd like to call out a few quickly. The top two benefits relating to HPC workloads that we get from containers are portability and software choice. Portability means the application is executable in a myriad of environments. Software choice means that the application can bring its own environment. Put these two together and we have a technology that allows us to forego the complexity of building applications for each environment by providing one technology that can run in many environments without the constraints of the machine software environment. Even though there are many benefits to containerization, there are some caveats. For instance, although the containers are portable among software environments, they are not portable on different hardware architectures without modification. For instance, if you moved an application from an x86 system to a Power 9 system, you would need to recompile the application and any needed libraries to match those environments. In the container, it's no different, so we have to create separate containers with specific binaries and libraries for each hardware platform. Additionally, certain HPC systems have specialized networking hardware and accelerators that are integral to achieving high performance in applications. Each type of hardware typically has its own libraries that are needed and sometimes need to match with the host system. Additionally, some devices require special support from container runtime environments like NVIDIA GPUs. This is compounded if you're using specialized hardware in addition to a non-typical hardware platform. For instance, the Longhorn cluster at TAC is using the Power 9 architecture, NVIDIA V100 GPUs, and InfiniBand networking. The primary consideration for any HPC project needs to be performance. If performance is not maintained, the value of our work is diminished. That being said, we want to reduce the complexity for the user, and part of that is making applications as portable as possible. So what are the performance overheads for containerization? My colleague and I have explored this topic at TAC with these research questions. Does performance of container-based solutions on HPC clusters match bare metal runs? And what are the challenges to building HPC clouds with container-based approaches? My colleague will now share what we found while looking into this important topic.
Thanks, Stephen. Hi, I'm Amit Ruhela and I'm a research associate at the Texas Advanced Computing Center. I will continue the presentation with containerization options and its performance on various hardware platforms. There are several containerization tools popular in the industry. We have chosen a bunch of popular options rather than doing an exhaustive performance survey as our focus is on performance and scalability on petascale clusters. Docker is the first well-known container implementation on commodity infrastructures. Docker is written in Go language and leverages Linux features such as namespaces to provide isolation to the containers, control groups to place limits on the resources, unit file systems to run containers within a single Linux instance, and avoiding the overhead of starting and maintaining virtual machines. Docker's image specification language has become an industry standard specification to build reproducible containers. However, Docker's approach is unfit for the HPC environment mainly due to the root privileges required to execute Docker containers and the associated security concerns. Singularity is a Lawrence Berkeley National Laboratory project that bind-mounts a container image and changes the apparent root to the container. Singularity goes a step further to support the HPC ecosystem by mounting native devices, example GPUs, network, IB, and configure file system paths while also preserving Linux namespaces and user mapping inside the container. Singularity doesn't require a daemon service but must be installed by the root user for privilege escalation. After building images on personal development machines or on HPC systems, if fake root is configured, users can pull images built with Singularity or Docker and safely run them on shared HPC resources. While images can be stored in the cloud, they exist as single files on a file system, allowing them to be shared and managed like all other files. Charlie Cloud is a user-defined software stack that exploits users and mount namespaces of Linux to run containers without needing privileged operations and daemons. Any packaging software capable of producing a standard Linux file system can build container images hosted on a private or public repositories. Charlie Cloud is a few thousand lines of open source code that demands minimal system control commands to configure computing facilities, which elude most security risks. Let's take a look at the experimental setup. In this work, we have evaluated containerization performance on 4 different clusters. The first cluster is IBM OpenPower plus NVIDIA V100 GPUs containing EDR100 interconnect. The second hardware architecture is Intel Broadwell and NVIDIA Quadro RTX 5000 GPUs with FDR56 Gbps interconnect. The third is the Frontera system with Intel Cascade Lake processors and HDR100 Gbps interconnect. And last is the AMD ROM system with AMD ROM processors and EDR100 interconnect. Let's take a look at the software configuration. In our setup, we have used Singularity with version 3.5.3, Charlie Cloud with version 0.21, and MPI libraries. One is MVPH2GDR version 2.3.4 and Intel MPI version 1907. Then we have used 2 microbenchmarks. One is Intel MPI benchmarks with 2019 update 7 version and OSU microbenchmarks with version 5.6.3. We have also evaluated the containerization performance with several scientific applications, one of which is MIMD Lattice Computation, which is a quantum chromodynamics code, and the second is VPIC, which is a 3D electromagnetic vector particle in cell code for modeling kinetic plasmas. Let's take a look at how we build the containers. We build the containers from the base images maintained at Tech GitHub repository for x86 systems and IBM Power AI Docker repository for open power systems. On x86 systems, we added benchmarks and applications by compiling them with base containers, and for open power systems, we added benchmarks and applications through overlay FS approach rather than building them from the manifest file. On all the systems, we use system MPI to launch the containers on the compute nodes. Let's take a look at the baseline performance of containerization techniques. We baseline the containers performance with MPI init micro benchmark. MPI init is a startup benchmark that measures average time each process takes to complete MPI init operation. We ran this benchmark with up to 6,144 nodes and we set ppn equals to 56. What it means, we instantiated 344,000 containers on 6,144 nodes. Here we find that Charlie Cloud incurs no significant overheads in containerization, initialization, and teardown compared to the bare metal runs. Next, we ran a MPI collective benchmark, that is MPI BCAS, where processes per node was set to 1. MPI BCAS is a collective benchmark in which one process sends a message to all other processes in a given communicator. The left plot in this slide shows the average latency of a broadcast operation at a given message size. The right plot measures the total time spent in running MPI BCAS benchmark. We observe that there is no difference in time to send a BCAS message at small, medium, and large message sizes between native and containerized runs. Whatever difference we see in the right plot are due to containers instantiation overheads, which slightly increases with the scale of the experiments. However, once the containers are initialized, native and container runs are on par on performance. We also ran the MP BCAS benchmark at full ppn, that is instantiating as many containers as the number of cores are available on a given processor. We identified that containerized runs at full subscription of nodes shows no significant performance overheads against bare metal runs at diverse problem sizes. After baselining the performance of containerization techniques with microbenchmark, we evaluated the performance of containerization techniques with scientific applications. We begin our experiments with MILC application, which is MIMD lattice computation on CPU nodes. Here we evaluated the time to solve the conjugate gradient, which is shown on the left side of this figure. We also evaluated the total time taken by the application and its memory consumption. We found that there is less than 10% overheads for containerized runs, which are mainly due to the containerized initialization and teardown at large system sizes. In practice, MILC is run for several hours instead of several minutes, which is shown in this figure. And therefore, the containerization overheads become negligible when it ran for a longer duration. Further, we also find that memory consumption for containerized runs and bare metal runs are identical at all system sizes. This is quite beneficial in case of containerization, which has significant performance benefits over the prior technique, which is virtual machines, which takes a lot of memory to run each instance of the virtual machines. We also evaluated the performance of MILC application on GPU systems, and here we ran the MILC application with up to 256 GPU nodes. So in this, we've identified that there are less than 4% overheads for containerized runs over bare metal runs, and memory consumption for containerized runs and bare metal runs are almost identical. Next, we evaluated the containerization techniques with vector particle and cell code on the CPU systems. And we found that performance of containerized runs is on par to the bare metal runs for both AMD ROM and Intel Cascade Lake systems. And while comparing the performance across AMD ROM and Intel Cascade Lake systems, we found that there is no architectural differences which alters the performance overheads across the systems. Similar experiment was conducted on GPU systems with up to 256 GPU nodes. And here also we identified that performance of containerized runs is on par to the bare metal runs, and architectural differences do not alter the performance overheads. Let's take a look at the lessons learned. Containers are often said to increase the portability of applications and offers an easy way to share application stacks. This is true in cases where necessary libraries or operating systems is slightly outdated or incompatible. They are often recommended to exploit massive tuning and optimizations realized within application containers by their developers. However, it is clear that containers portability is much murkier issue when working with different MPI implementations, CUDA versions, and platform architectures. As an example, containers built for x86 platforms are not compatible with Power 9 architectures. We conclude that if an application has a simple build instructions, it is better to install directly on platform instead of adding additional layer of containerization. Straightforward installations are much easier to profile and debug and with most of the utility and tools. Further, time-critical applications may be served better by direct installation for slightly better performance and predictable behavior. In summary, we can say that recent technological advancements in containerization runtimes have commenced a new trend of HPC software development, which has effectively reduced the deployment issues caused by complex software dependencies. In this work, we present the feasibility of state-of-the-art container technologies in HPC environment. Apart from the portability issues, we did not observe any significant performance overheads in leveraging containerized approaches. Neither we find any general security issues in HPC environment. We validated the on-par performance of Singularity and Charlie Cloud at benchmarks and application level on a large system with up to 644 compute nodes containing 0.34 million processing cores. We conclude that developers, testers, and end users can leverage containerization on HPC systems in a performant way at large scale to reduce software development and maintenance efforts. At the end, I would like to say thanks to all our listeners of this presentation. We would be happy to take any of your questions in person now, or you can send your questions offline at the email addresses given below. Thank you.